Good afternoon, everybody. I'll talk about some research work that I'm currently involved with. And this is joint work with three of my colleagues, Sridhar Narayanan, who's a PhD student of mine at the Institute of Mathematical Sciences, Digjoy Paul, who just finished his PhD from IMSC and is now a visiting fellow at TIFR, and Shraddha Srivastava, who was a postdoctoral fellow at my institute, and she's now at the University of Uppsala. Now, this work involves permutations. A permutation is just a rearrangement of some objects. So, for example, here you can see a permutation of numbers 1 to 5. So, in this permutation, 1 goes to 1, 2 goes to 4, 3 goes to 2, 4 goes to 3, and 5 goes to 5. Now, all these permutations put together form what is called the symmetric group. So we denote it by SD. It's the set of all permutations of the numbers 1 to D, and it forms, there are n factorial such permutations, and they form a finite group of n factorial elements. So these arise in nature whenever you have a system with n identical objects, then this would be a symmetry group of such a system. So it's very common, for example, in nuclear physics. So now, when we look at representations, they also come along with when we look at groups, they also come along with representations. So let me tell you some ways where representations of symmetric groups arise. So suppose you have a particle whose states are represented by some a vector space W. Then if you have D identical particles like that, then their combined possible states would be represented by the vector space W tensored with itself D times. For example, if you're looking at electron spin, then there are two possible states, and so the vector space that describes it is C squared. And now if you have 4 electrons, it would be described by C squared tensor C squared tensor C squared tensor C squared. So this would be a vector space of dimension 2 to the power 4, reflecting that there are 16 possible states for these 4 electrons. And now this, we can think of this vector space as a representation of the permutation groups. So you can permute these 4 electrons in 4 factorial different ways. And so, for example, okay, let's just take this example where we have 3 electrons. This is a little simpler. Well, okay, now I have 3 Cn tensors, Cn tensors. So I have a particle with n different states. And this dimensional vector space, and the symmetric S vector space by interchanging the three tensor factors. So among these tensors, you have the symmetric tensors which do not change at all when you permute the 3 components, and then you have alternating tensors which change under the sign of a permutation. When you interchange, say, 2 of the tensor factors, the sign changes. But then there's one more space which is a little more mysterious, and that I'm denoting by W 2,1 of Cn. So, and this space occurs with multiplicity twice, and that I've represented by something called V subscript 2,1. So what this 2-dimensional multiplicity space is actually a representation of the symmetric group. These subspaces of tensors will be viewed as representations of the group of all n by n matrices. So this is the general decomposition of tensor space. It was discovered more than 100 years ago by a mathematician called Isai Schur and popularized by the mathematician Hermann Weyl. And it's called Schur-Weyl duality. So it says that if you have this vector space C to the n, and you take its tensor power with it D times, then this vector space has 2 kinds of symmetries. So one is all the linear symmetries of Cn. So that's the group of all n by n invertible matrices. And the other kind of symmetry is the permutation group. So you can permute the D tensor factors. And so now you can ask, okay, so this is a representation of the group. Can I break it up into the smallest possible subspaces which are invariant under all these transformations? And the solution to that problem is given by the Schur-Weil duality, or the Schur-Weil decomposition, I should say. And it says that this tensor space breaks up into a sum over all partitions of D. So what is a partition of D? So a partition of 3 is like a way to break 3 up into smaller numbers. So 3 has 3 partitions, namely 3 is 3 itself, or 3 can be written as 2 plus 1. We will not distinguish between 2 plus 1 and 1 plus 2. It's the same way of breaking up 3 into 2 parts. And then 3 can be written as 1 plus 1 plus 1. So there are 3 partitions of 3. In general, this lambda would run over all partitions of the integer D, and we would have these pieces which are made up of what are called Weil modules, W lambda, and spect modules, which are the V lambda. So these V lambdas are the irreducible representations of the symmetric group, and W lambda are the irreducible representations for general linear. So there's a parameter here, n, which is the dimension of the vector space. Okay. So how do we work with representations? So the signature of a representation is what is called its character. So the representation is given by a matrix, and you just take the trace of this matrix and think of it as a function on the group. Just as atoms and molecules in spectroscopy are identified by the wavelengths of light that they absorb, representations are understood by studying their characters. And this is more than a poetic analogy. In fact, in spectroscopy, what you observe are values of the characters of the symmetric group. So now, what I'm trying to do is to solve certain combinatorial problems in representation theory. I'll mention 3 problems. The first one is a well-known solved problem. So you have 2 representations of the general linear group, and I already mentioned to you that these are the Weil modules. So they are indexed by partitions, and this n is the parameter. So they have W lambda Cn, W nu Cn, and if you take their tensor product, how does it decompose into irreducible representations? So this is the Littlewood-Richardson problem, and these have been known for a long time. They were conjectured by Littlewood and Richardson. These constants given in red here, C, lambda, mu, nu, are the multiplicities, and there's a result due to Lasko and Schützenberger in 1980. They proved the Littlewood-Richardson rule, which basically tells you, gives you a way to construct a set whose elements you can count, and once you count them, you will know the multiplicity of any representation of GLN in a tensor product of 2 other representations. So this is one of the greatest achievements of algebraic combinatorics, the Littlewood-Richardson rule, and its proof itself has led to very, very beautiful ideas in algebraic combinatorics. But the 2 open problems that I'm working on, one of them is called the Kronecker problem. It's a notorious open problem, and people have been working on it for many years, and I am not, we are hoping not to solve the problem completely, but rather to make some progress towards it. So here you take 2 representations of the symmetric group and tensor them, and then you ask how does it decompose. And there's a third problem, perhaps not so well known, but I feel equally tricky and interesting, which is the restriction problem, which is that you take a Weil module, a representation of n by n matrices. Now inside the n by n matrices, you can look at permutations. You can think of a permutation as a matrix by thinking of it as a matrix which performs the corresponding permutation on the coordinate axes of the vector space. So you take this representation of GLNC and restrict it only to these matrices, and you get a representation of the symmetric group. And then you can ask, how does it decompose into irreducible representations of the symmetry? So these are the 3 problems that, well, the last 2 problems, the second and third problems are the ones I'm working on. And how do we approach this problem? So I'm using a technique. So basically, firstly, we need to understand what a permutation looks like. I call this the anatomy of a permutation. So you look inside a permutation. So the permutation that I had given you as an example earlier, you can think of it as, you can draw it somewhat differently. In this permutation, 1 goes to 1. So I've drawn an arrow from 1 to itself. 2 goes to 4. Oops. I think I've drawn this arrow backwards. 2 goes to 4, 4 goes to 3, and 3 goes to 2. I have the arrows backwards here. And 5 goes to 5. So when you look inside this permutation, you see it breaks up into what are called cycles. In this example, we have 1 3 cycle and 2 1 cycle. So now a permutation is just a rearrangement. I'm going to associate to this permutation some statistics. So x1 is the number of 1 cycles, x2 is the number of 2 cycles, x3 is the number of 3 cycles, and so on. So these are permutation statistics, and they have very interesting properties. For example, if you take a large random permutation, then the random variables x1, x2, x3, and so on are independent Poisson random variables with expectation 1 half, 1/3, 1/4, and so on. Okay, so now I mentioned already that if you have a representation, we're going to study it using its character, which is basically the trace of the matrix. And an important point is that this trace depends only on the cycle decomposition on W. So it only depends on the number of 1 cycles, the number of 2 cycles, the number of 3 cycles, and so on. And so the idea is to use polynomials to write down characters of the symmetry. So given any polynomial in infinitely many variables, x1, x2, x3, well, a polynomial is still going to be a finite sum, but we don't put a limit on which variables you can use. Then it gives rise to a function on the symmetry group for every n. So it gives you an infinite family of functions on symmetric groups, which we think of as virtual characters. They may not be characters of representations, but sort of their formal linear combinations of characters. And there are formulae for these. There's a classical formula for the character of an irreducible representational symmetric group. I'm just flashing it here. It probably won't make, it's not enough time to explain what all these terms mean. This is the Q lambda up here. And in our work, we have also derived characters for the restriction of while module to the symmetric group. And it's given by this capital S lambda, which is a determinant involving some characters called, some polynomials called H lambda, which are determined using this formula here, whatever it means. Okay, so we have these formulas, and another thing that we need to do these character calculations is we need to know how to average the values of characters over symmetric groups. And once you do that, you can express constants which are the problem and the restriction problem in terms of these polynomials that we have found formulas for and this averaging function. So how does this averaging function work? So it's so we have this polynomial in many variables, and I use this notation xi choose ai to denote a polynomial in the variable xi, which is given by this formula. It's xi x multiplied by xi minus 1 dot 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 up to xi minus ai plus 1 divided by ai factorial. And you multiply these over all ai, and this gives x choose alpha. Now, if you look at this polynomial in the variables x1, x2, x3 for some fixed alpha, then its average is going to be given by this very simple formula. So this is another result that we were able to prove. It's quite easy, in fact. And combining these things, the formulas for the character polynomials, q lambda and s lambda, and these moments, we can actually get some information about the restriction problem and the chronicle. I'll talk more about the restriction problem here. So we can get, for example, beautiful generating functions to find out the dimension of the Sn invariant vectors in a while module, which is a special case of the restriction problem. We can also find the multiplicity of the sign representation of Sn in a while module using another generating function. And these two generating functions are very similar looking. There's some changes of sign, something moves from the numerator to the denominator. They're basically bosonic and fermionic versions of the same formula. So And we found that through these generating functions that these restriction coefficients are closely related to counting vector partitions. So what's vector partitions? Given a vector x, we are assuming that the coordinates are non-negative integers. So we're going to use bold N to denote the set of non-negative integers. A vector partition is a way of writing this vector as a sum of other vectors. Just like I talked about integer partitions, the ways of writing an integer as a sum of other integers, vector partition is a way of, and here everything has to be non-negative. And so this number of such decompositions is going to be finite because all the terms have to be non-negative. And this is called the vector partition function. Okay, so the one variable case is very well studied. It's the theory of integer partitions, and there's a famous formula of Hardy and Ramanujan, which started off a whole area of analytic investigation, where they estimated how fast this grows. But such methods are not available to study vector partitions because of the lack of something called modularity. So, but in any case, we have these formulas show up. So in the restriction problem, the dimension of the space of Sn invariant vectors in a while module is given by an alternating sum of these vector partition functions. So for example, if you take a while module corresponding to a partition with just two parts, so W lambda 1 lambda 2, then it's given by a difference of two. So these are just partitions of a vector with two coordinates, lambda 1 comma lambda 2 minus lambda 1 plus 1 lambda 2 minus 1. So you increase one of the coordinates by 1 and decrease the other coordinate by 1. And here, lambda 1 is greater than lambda. That's the convention for writing partitions. So what this means is that if lambda 1 is greater than or equal to lambda 2, then Pn of lambda 1 lambda 2 had better be greater than or equal to Pn of lambda 1 plus 1 lambda 2 minus 1, just because their difference is the dimension of some vector space. I'm sorry, this should be the Sn invariant of W lambda 1 lambda 2, not W lambda 1. Okay, so what this is doing is it's giving a unimodality result for what are called bipartite partitions. So in the table, I've written down number of vector partitions of vectors, the rows lambda 1 comma lambda 2, where lambda 1 goes along row, lambda 2 goes along column. And what you see is that the number of vector partitions along each diagonal parallel is maximum along the principal diagonal. So that means, for example, here, P8, 5, 8 is closer to 5 than 9 is to 4. So P8, 5 is greater than or equal to P9, 4. And the reason is that difference, 831 minus 608, is the dimension of the Sn invariants of the while module. Oops, again, here I forgot to say Sn invariants of the while module of 8, 5. So there was a different proof of this result already known, but this is a much more natural proof of this result. We have other positivity results. For example, we're able to characterize in many infinite families of partitions when the trivial representation and the sign representation occur in a while module. And we are continuing to work on this, and we're hoping that we will be able to get stronger results eventually. So that's all I wanted to say.